So this is Math 2020 Lecture number 42, in which we continue coverage of section 11.10. Okay, so let me remind you of where we are. Last time we had a function. We started with a function. We started with a number x equals a. So we are looking at Taylor series at x equals a. And we are considering. So let me remind you what that looks like. So we have the Taylor series is the expression t infinity of x given by f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared, and then we have to divide by 2 factorial, and so on. F third derivative at a over 3 factorial x minus a cubed, etc. And so this is in compact form, the sum, k goes from 0 to infinity of the kth derivative at a, x minus a to the k, and then there's a k factorial. Okay. So that's the expression, and what we want to know, we also have the nth Taylor polynomial, which is the truncation of this series at stage n. So we look at the sum from k equals 0 to n of fk of a over k factorial x minus a to the k, and then we had the nth remainder, which is Rn of x, which is defined as Tn of, as the function minus Tn of x. So there's the nth remainder. And this is the nth Taylor polynomial over here. Okay, and we're interested when does f of x equal t infinity of x on some interval near x containing a, on the interval a minus d, a plus d, for some real number d. So that's what we want to know. And we actually have a criterion which we can use for possibly deciding this sometimes. Here, d should be some number which is at most the radius of convergence. Here, r is the radius of convergence of the Taylor series. Okay, so let me remind you what the Taylor theorem says, the Taylor approximation theorem, or the inequality. So the statement is this: let's suppose that the nth plus first derivative, here we're assuming f has all the derivatives that it can possibly have, is bounded above by some number m on the interval a minus d, a plus d. It's an open interval, and this number m, I should point out, will depend typically on the number n that you're looking at here. It could be different from different values of n, but in any case, the statement is this: then the nth remainder, which is like the error term in absolute value, is no more than m over n plus 1 factorial times x minus a to the nth plus first power. So this is actually a very important result, and this is on the interval a minus d, a plus d. Okay. So let me make some remarks about this. In order to do that, I have to save this screen. Okay, so here's a remark. If Fn plus, if we can find a bound for all x, for all n, for every n, so if we can find some number m which bounds all the derivatives, then if we use the formula, if we stare at the formula, Rn of x is at most m times x minus a to the n plus 1 over n plus 1 factorial. Since m is not changing when n varies, this limit will go to 0 as n goes to infinity. So that implies that the remainder tends to 0. And by the way, this is on the interval a minus d, a plus d. So then the remainder tends to 0 on that interval a minus d, a plus d. And that means that f of x equals t infinity of x on the interval a minus d, a plus d. So all we have to do is find a bound for all the derivatives, and we're guaranteed that the function is equal to its Taylor series. And that answers the original questions if we can actually find this bound. Okay, so let me consider. Let me make a remark also. Another remark. This section is called Taylor and Maclaurin series. So let me just point out the Maclaurin series is just the Taylor series. It's a special case when a is allowed to be 0. When a is the 0, we're centering it at 0. So that's what the Maclaurin series is. So let me make this cleaner. Okay, so this is enough of theory today. What I'm going to do now is just some examples. I'm going to do 3 examples. So I want to consider the function sine of x. So that's f of x. And I'm going to look at the Maclaurin series. I'm going to look at a equals 0. So what are the derivatives of sine x? Well, there's f prime of x, which is cosine of x. There's f double prime of x, which is minus sine of x. And then there's the third derivative of x, of f of x, which is minus cosine of x. And then when you get back to the fourth derivative, you return. It's a fourfold periodic differentiation. You get back to sine x. Now, in order to write down the Taylor series, we need to evaluate these derivatives at a equals 0. So we have f of 0 we need to know. Well, that's a sine of 0, which is 0. There's f prime of 0, which is f prime of with cosine of 0, which is 1. There's f double prime of 0, which is 0. There's f triple prime of 0, which is minus 1. And there's the fourth derivative of 0, which is 0. So it alternates. It either has value 0 or plus or minus 1, all the derivatives. So from this, we can actually write down what the t infinity of x is. What is t infinity of x? Well, it's f of 0, which is 0, plus x, 1 times x over 1 factorial. Then the x squared term is vanishing. Then there's a minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, etc. Minus x to the 7th over 7 factorial, dot, 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 dot. In other words, you can figure out what this is in sigma notation. It's going to be given by summation. N goes from 1 to infinity of minus 1 to the n minus 1 times x to an odd power to the to n minus 1 is an odd number, and n is starting at 1, so you're going to get x to the first power starting, and then you have to divide by 2n minus 1 factorial. So that is the Taylor series. Now we want to know convergence. Convergence is easy. The radius of convergence can be computed. So by the ratio test. So we have to take the nth plus first term, that's an plus 1 over a sub n, absolute value. So what is that? You're going to get the absolute value of minus 1 to the n plus 1. I have to replace n by n plus 1 in the expression, times x to the 2n quantity plus 1 minus 1, so that's 2n plus 1, over 2n plus 1 factorial. That's a sub n plus 1. And then we have to multiply it by the reciprocal of a sub n. That's 2n minus 1 factorial over minus 1 to the n minus 1 times 2n minus, times, oops, that's a mistake, times x to the 2n minus 1. So this simplifies to, the signs go away and you're left with x squared times 1 over 2n plus 1. The factorials cancel except for the first two terms in the product for the factorial of 2n plus 1 factorial, so it's 2n. So no, and there's no absolute value anymore because everything is non-negative. And as x is, so this term here will always shoot off to 0 as n goes to infinity. So this always converges to 0. So by the ratio test, the radius of convergence is infinity. So it converges for all x. This series converges for all x. Now I want to apply the remainder formula, this Taylor approximation formula. So we need to find a bound for all the derivatives on some interval, a minus d, a plus d. Here, d could be any real number that we want to choose to make it work. So I can even choose, so let just d be any real number. And here a is 0, so it's really minus dd. So so on minus d comma d, for some real number d, what do you have? Well, we know that the nth remainder is less than or equal to m. What is m? Well, it's a bound for all of these functions, cosine x minus sine x minus cosine x minus, on the interval from minus d to d. But the number 1 always is a bound in this case. M equals 1. So we get 1 times the absolute value of x to the n plus 1 over n plus 1 factorial. And we know this goes to 0. So therefore, we know that f of x equals t infinity of x on minus dd, but d was arbitrary. D was any number you handed me. So this is going to be true for all intervals. In other words, it's for all, i.e. for all x in the real numbers. In fact, this works. So we get that the sine function is equal to its Maclaurin series everywhere for all values of x. Okay, so that's example number 1. I want to turn to example 2. So that's f of x equals cosine of x. This is actually very similar to what we just did, except f of x here is cosine of x. F prime of x equals minus sine of x. F double prime of x is equal to minus cosine of x. F triple prime of x equals minus plus sine of x, actually. And the fourth derivative, you get back to where you started. So, and here I'm going to choose a equals 0 here for the Maclaurin series we're going to get. Okay, so what does that tell us? That tells us f of 0 is 1, f prime of 0 is 0, f double prime of 0 is -1. The third derivative is 0. Every odd derivative gives you a value of 0. And then finally, the fourth derivative gives you back 1. So this tells you that T infinity of x, in this case, the Maclaurin series, is given by 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, etc. In other words, its sum, n goes from 0 to infinity, of -1 to the n, x to the 2n over 2n quantity factorial. So the same analysis as we did for the sine function, the same analysis shows that the same argument essentially shows that f of x in this case, well, let me write sine x. Sine x is equal to this converges everywhere, and sine x is equal to its Maclaurin series for all x in the real numbers. So we represented sine x as a power series. Okay, so let me go to our final example. Okay, so this is example 3. This is called the binomial series. Okay, so here's what we're going to look at. We're going to look at f of x equals 1 plus x to the power of k. And k here is some fixed real number. It could be an integer, for example. Okay, so now we've handled cases like this. If k equals -1, we get 1 over 1 plus x, because 1 plus x to the -1 is 1 over 1 plus x. Okay, let's start computing now. We're going to do this at a equals 0 again, the Maclaurin series. So we have to compute derivatives. So what is f prime of x? F prime of x is k times 1 plus x to the k minus 1 times the derivative of the inside, which is one derivative of 1 plus x, but the derivative of 1 plus x is 1. Okay, so that is f prime of x. What about f double prime of x? That is k times k minus 1 times 1 plus x to the k minus 2. What is the third derivative? That's going to be k times k minus 1 times k minus 2 times 1 plus x to the k minus 3. Well, you get the pattern. The nth derivative of the function f at x is given by k times k minus 1 times k minus 2 dot, 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 dot. And if you see what goes in here, it's k minus n plus 1 goes here times 1 plus x to the k minus n. That's the nth derivative. That makes sense. Okay, so now we can evaluate the derivatives at a equals 0. So f of 0 is just 1. F prime of 0 is k. F double prime of 0 is k times k minus 1. Dot, 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 dot. The nth derivative of f at 0 is k times k minus 1. Dot, 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 times k minus n plus 1. This big product. And this is going to be true for any real number k. Okay. So let me point out that the special case when k is a positive integer, we can actually rewrite this expression as the binomial, as the k factorial over n factorial, but this will only make sense if if n is less than or equal to k. So this is the special case here that you can write it like that, right? So that's what you get, because k factorial is the product of the integers 1 through k. N factorial is the product of integers. Oops, I didn't say that right. It's k factorial over k minus n factorial. Oops, that's a mistake I did. Okay. Okay, why did I do that? Well, because then if we look at Fn of 0 over n factorial, which is the coefficient in the Maclaurin series, we get k factorial over n factorial times k minus n factorial. And this is the so-called binomial coefficient k choose n. Okay, so this is the binomial coefficient k choose n by definition. Okay, so k choose n is k factorial over n factorial times k minus n factorial. So this actually even makes sense if we define it in this particular way as the product of the integers, the numbers k, k minus 1, all the way to k minus n plus 1, divided by n factorial, divided by n factorial. So this is, in other words, we could have defined it for any real number using this expression, which makes sense for any real number. In any case, what this tells us is the following. If we now write down the Maclaurin series, so T infinity of x is equal to I'll just write it out. Summation n goes from 0 to infinity k choose n x to the n. So this is called the binomial series. It converges when absolute value of x is less than 1. And in this case, it can be shown, but I won't show it, that 1 plus x to the k actually equals the binomial series whenever this is true. Okay, so this is what I wanted to do as an example. Okay, so let's take a special case. Here, I'm going to take two special cases, in fact. So special case. So we can look at k equals -1. So on the left side, you get 1 over 1 plus x. And what happens on the right side? Well, we have to look at the sum, n goes from 0 to infinity, of -1 choose n, x to the n. So we have to figure out what -1 choose n looks like. Okay, so what is that? According to the definition, that is equal to -1 times -2 all the way up to minus n divided by n factorial. And this is, the numerator is n factorial up to sign, and the sign is -1 to the n, I believe. So you get -1 to the n. So in this case, the sum in question becomes the sum n equals 0 to infinity of -1 to the n, x to the n. But that's what we know, that's a geometric series, and we know that with common ratio minus x, and we know the sum is 1 over 1 plus x. We saw that already way back when. So the case k equals 1, it was already known to us. Okay, so that's one special case. And here's another special case, which is less interesting. k equals 1. So you're going to get on the left 1 plus x. 1 plus x is equal to summation n equals 0 to infinity of 1 choose n, x to the n. Now let's figure out what 1 choose n is. Well, we'll do it over here. 1 choose n is given by, it's given by 1 times 0 times minus 1 all the way up to 1 minus n plus 1 over n factorial. This actually has a 0 in it if n is greater than or equal to 2. If n is less than 2, it's actually equal to 1. Okay, so this is actually going to vanish if n is bigger than or equal to 2. And if n equals 1, 1 or 0, then you get uh, 1 choose n is equal to 1. So what this is saying is that the right side of the equation is equal to, there are only two terms and it's 1 plus x. Well, 1 plus x is 1 plus x. There's no information in the binomial series in that case. Okay, so that's it. There you have it. And you could do one more special case, I guess, which is the case k equals 2, which is probably enlightening. So let's take the case k equals 2. So then we get 1 plus x squared is supposed to be equal to the sum, choose n, x to the n goes from 0 to infinity. So let's figure out what 2 choose 0 is, 2 choose 1 is, and 2 choose 2, we know that. These we all know because 2 choose 0 is the binomial coefficient is going to give you 1. 2 choose 1 is 2. 2 choose 2 is 1. And 2 choose 3, all the higher ones are 0 if n is bigger than or equal to 3. So this is 1 plus 2x plus x squared. Well, we know that already from the binomial formula. So the binomial series generates the binomial formula. Okay, so that's it for today. And we will still continue with finishing off 11.10 next time in my next lecture.